At Kew Gardens, they're very proud of having found a new species of giant Amazon water lily. And they have this in their tropical greenhouse. So even though it was November and it was rather wet and chilly outside, the tropical greenhouse was just full of the most beautiful tropical flowers, including orchids. Some of them were almost as good as the orchids we have at Jurassic Ark. But the thing they were particularly proud of this time was this giant Amazon water lily. And you may have heard of this. It's rather an iconic sort of plant because it has these enormous leaves. They're the biggest leaves in the world. They are really huge. And you can see here how they compare to the size of the ordinary water lilies or the other water lilies. And these large leaves are an interesting uh, study for scientists, because they have looked at these things and say, well, why did this plant grow such large leaves? Well, there are advantages in that having large leaves is a large surface area for photosynthesis. In other words, that's how the plant gets its first basic nutrients from the sun. So leaves are basically just giant solar panels, far more complicated than any solar panels that we've ever designed. So the bigger the leaf area in a plant, the bigger the surface area for photosynthesis. So the individual water lily leaves really are very good for feeding this plant. However, you have to there is a disadvantage, of course, in that the bigger the leaves, well, you do have a larger leaf mass and it's quite heavy and it uses more of the plant's resources to maintain. So a couple of years ago, scientists based at Oxford University decided that they would actually study this, and they looked at these leaves in a lot more detail. Now, you can see here, this is another plant. This isn't actually at Kew Gardens, but this photo does show you the sort of trellis work um, that lies underneath these leaves that literally holds them up. And this is the pattern of veins. Now, all leaves have veins. Sometimes they're more obvious than others, which is the internal plumbing for the leaves. But it's also the structural support of the leaves, because the walls of the internal plumbing, of the pipes, as it were, are stiff, and that is what holds the leaf up and what gives it its structure and its shape. And that applies to all plants. So it's the same with these giant leaves, but they need a particularly strong set of plumbing, as it were, or structural framework in order to hold these leaves up. And as we know from architecture and engineering, it's not just the amount of mass that you have in a structure that makes it strong, it's also the architecture and the geometry. So scientists have studied the geometry of these things, and if you look on the back, you can see there's this particular trellis-like pattern. And they looked at this pattern and measured the strength of the substances that make up this, and put that all into a computer model, and worked out that this really is a piece of brilliant architecture in terms of getting the right combination of something that is extremely strong but also lightweight. And to get something that is very strong but also lightweight takes quite clever engineering design. And so they found that these large leaves had this amazing network of veins, which was very strong but very light. Now, there is also a problem with leaves growing on in riverbeds or rivers where they grow in the wild, in the Amazon, in that in these rivers you have wading birds and water creatures. Now, with small water lily leaves, that's not a problem. They just sort of push them aside. But these big ones, they do tend to be damaged if wading birds and other creatures come into them. But you can see how the edges of them are actually are standing up. And in fact, you can see the pattern of the veins there, but there is a distinct folded edge so that they don't completely become flat. Now, they do start out um, sort of partly rolled up, and here we are back in Kew Gardens now, and you can see there's a new one that's just emerging from the stem there, and it's starting to unroll. And they don't completely unroll. They have this standing up edge there so that they are not damaged by water birds and by other creatures. And you can see there's a distinct fold there in the structure. And that has to be programmed into the leaf, so as part of the control of its growth. So they are flexible, so that avoids being damaged by birds and by other things that live in the river. Now, because they have that vertical, that rim there, there is a bit of a problem. The Amazon is a place where there is a lot of rain, and these things grow in a rainforest, and so water will just run off small leaves, but it will be trapped by the folded edge of large leaves. So you can see there's a normal water lily leaf there, which is just completely flat. Rain will run off that. Um, However, that has also been taken care of in the giant water lily leaves. The large leaves actually have holes in them um, for rain drainage, so that they don't fill up with rain and then sink. So it's often in these very, very little things that you see the sort of foreknowledge that's needed for clever design. So the large leaf design involves the network of veins that's very strong and very light. It's very flexible, and it has holes for the rainwater to flow through. And the scientists who looked at the structure of these things published their study earlier this year, and they said, we show that the geometric form of the leaf is structurally more efficient than other smaller species of water lilies. In other words, it has all of these extra features. So you then have to ask, well, where did it get those extra features for? Well, it had to be in their DNA and in the growth control genes that not only make the leaves grow bigger, but also have those extra features to make them more efficient. And as we know, merely just knocking the chemicals around in your genome does not actually produce anything new or better. It actually causes information to be lost. So new genetic information is needed if you're going to make these water lilies in your evolutionary idea that these evolved from another type of water lily, whereas in fact these have always been the same kind as far as we know. And one of the Oxford scientists made this comment: remarkable structures in nature can help us unlock design challenges in engineering. And the form of these water lilies could inspire giant floating platforms such as solar panels in the ocean. There's a lot we can learn from leaves. Now, just a moment, who are we learning from? Yes, we can learn a lot when we study leaves, but what we see is really clever design engineering and clever genetic information that has been inserted into these water lily leaves. So we're not learning from the leaves, we're learning as we look at the leaves, but ultimately, we should be giving the honour to the Creator who made heaven and earth and all that is in them, including the holes in water lily leaves and all of those little things that show you the brilliant forethought that's gone into these. So even though Kew Gardens might be claiming, oh yes, we found a new species of giant Amazon water lily, they are all still giant Amazon water lilies. What they found was a bit of variation in the structure of the flowers. The leaves are all the same. So these are still the same kind. So these water lilies are their own kind. They have multiplied after their kind. there is a bit of variation, but as we show in our Jurassic Ark site, you can get tremendous variation within the same kind. And as you look at these, we see brilliant design and we see after their kind. In other words, we see what the Creator has told us in Genesis, who created all things according to their kinds.